Alright, if you thought what we did was crazy, making a plane, making a surface, and then also defining things that are in both of these lines at once as complex numbers, which is a terrible name, let's accept that as well, that you can represent any 2 points, a plus a bi, on this. A and b both being real numbers that you multiply times I. Well, this one you multiply times I. So this is a complex number. Alright? Yeah, cool. So what can we do with this plane? I don't know. Let's talk about planes in general. How about this? Not only planes, but airplanes. Woo! So, actually, no, let's not talk about airplanes. That was going to be funny, but... Alright, let's talk about navigating New York City. NYC. Alright? You have two choices, alright? Your two choices are to go by cab or to fly with a pigeon. Alright? And you need to get from where you are, and let's say 4 blocks this way. 1, 2, 3, 4. And 3 blocks this way. 1, 2, 3. So you want to get to this point on your map. Well, let's take the taxi cab. Well, let's say these technically New York City streets are way more rectangular than they are, than they are just straight on. But let's talk about this for a second. So, you could tell your taxi cab driver to go just 4 blocks to the east, sorry. This would be east and this would be north. So 4 blocks east and then 3 blocks north. Alright, nice. And then you got to your destination. But there's another way to get to the exact same point, isn't there? So we checked out what the cab would do. I mean, the cab could zigzag, but in essence, this is what it's doing. It's just going these blocks forward and these blocks north. Alright, so let's see what the pigeon would do. Well, the pigeon doesn't have to obey the streets. The pigeon can just fly straight there, can it? So if you tell it its direction, right? And by the way, this direction for this particular triangle, I think it would be like 54. I think it's about 53. Yeah, I remember now. It's about 53.1 degrees. I would work in radians in this video, but I feel like degrees are a little more sensible at the moment. So if this is 53.1 degrees, the last thing we need to tell it, I mean, this is 53.1 degrees north from east. Let's say just north. Alright, because that's a direction. We're just talking about direction right now. And then you just have to tell it how far to go in that direction. Well, you can use basic Pythagorean theorem here, but there's a reason I picked 3 and 4. It's because it multiplies and adds together to equal 25, and then they square root to get 5. This is a perfect triangle. Oh, not north, just in the direction of 53.1 degrees north. And that's not the exact direction. That's just a very close approximation. Alright, so those are the two ways to talk about a distance. You could talk about it as 3, 5, or you could talk about it as a distance of 5 and an angle of 53.1 degrees. Or, in vague sense, A and B, or, let's say, an R and an angle. And if you're used to these, there's Cartesian, just if you want to put a name on it, Descartes, and this is polar. Think pole rotation. Alright, so you can talk about any point on a plane as an angle and then a distance to that point, or as a distance right and a distance up. Yeah, and negative distances right would be left, and negative distances up would be down. Cool. So this interesting, but what does it have to do with these numbers? Oh, you're probably thinking, I could I could represent any point, Cartesian or polar, the same way with this guy. So we could represent any point on this plane as a plus bi, or we could have an exact same representation that was a radius, and then this is how to write it, an angle. It's truly astounding, except for it's not that astounding. It's not bizarre to say that these get you the same value. But it's interesting. In fact, if you want to know the formula that you use to convert from the exact formula, this is just a way to represent it. But technically, you just say r e to the I angle. Technically, this is your formula right here. Don't worry about why exactly at the moment, but just know that this gives you the exact same value as a plus bi. Alright, I'll stop talking about that because I don't want to give away too many things. So let's move on here. Let's talk about let's talk about cosine and sine. Alright. There's going to be some trig review. You probably already know it, but we're going to need it. So let's talk about converting from polar to Cartesian. Alright. So we know that on a unit circle, if you have a distance of 1, this distance right here is exactly cosine of your angle right here. This distance right here would be exactly sine of your angle right there. So cool. These only have to be defined by an angle alone. Now if you have another triangle, like your New York City triangle of 5, all you have to do is multiply every side by 5. So this angle was equal to 53.1 degrees. So this is 5 times sine of 53.1 degrees. You can try this in your calculator. You should get it. Make sure you do degrees. And 5 times cosine of 53.1 degrees. Alright, perfect. And that's how you can talk about triangles. Such, you know. So that's how you convert from what we'd say polar, this r angle theta, to a b. And in essence, r theta, what we did is we just multiplied everything by the distance. So we have r times cosine of the angle would be your x piece right here, your real piece. Then your imaginary piece over here would be r times sine of an angle. Guess what? Times I. This is all very interesting. Let's use it to derive a simple formula, alright? But also a very useful one. So let's talk about only distances of 1 in the complex plane, alright? And why are we working in the complex plane? Well, again, I like to think of it as the I forces a number to be in another direction. Which sounds amazing, but that's really all it does. It just forces a number to be on another line, which is quite useful. So let's talk about a circle of 1. So a unit circle right here. Let's draw it. No, this is awful. And it's also kind of small. So there's our circle. Looks a lot more like a oval, ellipse, or whatever. We can work with it. If you take, let's think here. If you take positive 1 and multiply by itself and square it, what do you get? Positive 1. Cool. So if you take this point, it brings you back to yourself. Cool. Now let's take negative 1 and multiply by itself. We already know what this is equal to. Negative 1 times negative 1. The negatives cancel out. You get positive 1. So we know that this point takes you to this point. And now, let's go here. Let's see where this takes you. So we know that I is the square root of negative 1. So if you square it, you get negative 1. So this point brings you to this point. Alright, and how about negative I? That's just going downward. Well, negative I squared is the same as not having a negative in the first place, right? The negatives cancel out, and so you just get negative 1. So that's I squared. So this point down here brings you to this point as well. Why does this make sense? Let's think. So if you take a point right here, this is technically 0 degrees from the origin, right? We always say that this is our 0 line. And so 0 degrees plus 0 degrees is still 0 degrees. Or you can think of it as 360 plus another 360 brings you to the exact same point. You're not rotating any bit. Now this point is 180 degrees, so if you square it, multiply by itself, 180 plus 180 is 360. Or you can think of it as this is 180, this is negative 180, add them together, and they cancel out to 0. You can think of it as any of these circumstances. There's infinite angles that get you to that exact same point. But no matter what those angles are, they will always add to themselves to get you to this point when you rotate it. Now what's interesting about this one, this is 90 degrees. So if you multiply by itself, 90 degrees plus 90 degrees is 180, bringing you to here. If you think about this one, you can think of it as two ways. You can think of it as negative 90, so negative 90 plus negative 90 brings you to this guy. Or you can think of it as, that's 90, 90, 90, 270. 270, if you take this whole angle piece and add it to itself, it brings you to this point. So there's a reason. This is telling you something. This is telling you that if you take a complex number and you square it, that's the same as adding its angles together. Almost done together. And even more interesting, you don't have to square a number. If you multiply two different complex numbers, let's call it C1 and C2. Let's say C2 is 1 right here, and C1 is I. I don't know why I said that backwards. Alright, so if this is I times 1 is I. That makes sense because 1 is 0 degrees. 0 degrees plus 90 is 90 still. It stays at that point. So that is why multiplying by 1 doesn't change the value of a number, because it adds no angle to that point, basically. Or adds a full rotation to that point, which gets you in the same spot. There's also another thing that happens. Let's say we multiply 2 by itself. 2 times 2 squared is 4. So its distance multiplies by itself. So 2 squared is 2 times 2. So that's technically two different complex numbers right here, just without an imaginary portion. 2 times 2 giving you 4. So we find that the distances are multiplying. Let's totally make sense of this. So we know that negative 2, if we square that, that gives you positive 4. So we know that gets you positive because it's 180 degrees plus itself. Let's talk about negative 2 times negative 3, though. That's also positive because both of these are at 180 degrees from each other. Well, from the 0 line, basically. This line right here. Alright, so we know that the angles add together. We can accept that. We've basically proved it. And now the distances multiply. So what does that equal? That equals 6. That multiplies. Let's talk about, how about 5i? 5i times 5i is 25. And I times I is negative. So we understand the negative. That's just the rotation portion. Now why is it 25? Well, that's the distance multiplied by itself. And so if you had two different complex numbers, yeah, sure. Now let's do something a little more complicated. Let's first talk about what this distance is. Here, I really like working with 3 plus 4i, because we know that's a distance of 5. How do we know it's a distance of 5? Let's check. What we do is we take the square of 1, the first one, that's 9, and take the square of the second one, that's, I meant to say square, not square root. Square of the second one is 16. Add them together, you get 25, and we know the square root of 25 is 5. Now, this confuses some people sometimes. It's because, I don't know, this confused me for a long time, that this is what's known as the magnitude of an imaginary number. That any distance is still the same amount. And why is it this formula? Why is it not minus? Seems like minus would make sense. I mean, if we can accept negative square roots, we can accept imaginary magnitudes in a sense, really. But here's the thing. If we square this number, we actually don't, we ignore the I. because we care about the literal distance. The literal distance is 3 and 4, not 4i. I is just the component that gives it the direction in this direction. 4 is the actual value of it. So we only square 4, not I. If we squared I, then we would have a negative here, but we don't. So we know we get a distance of 5. Good. And so, if you multiply 3 plus 4i by itself, you should get a distance of 25. Let's check. If you square it by itself, you get 3, 4i. Let's do box method. And 3 and 4i. I times I is negative. 4 times 4 is 16. 4 times 3 is 12. There's only one I here. 3 times 4 is also 12 on I here. And then 3 times 3 is 9. So 9 minus 16 is negative. Let's see here. If you remove 9 from that guy, you get 7 plus 9 is 16. So negative 7 plus 9. Well, negative 7 minus 9 should give you negative 16. Good. So yes, you get negative 7, and then 12i plus 12i is 24i. Let's imagine where this is on the complex plane really fast, just to check that the rotation thing is true, because we're picking an actual complex number, a combination of points. So 3 and 4. That would actually be closer to that if that's 3. So that's going to be our point there. Alright, and we multiply it by itself, so we expect an angle to be somewhere like this. Let's check. Negative 7, that's slightly longer than this. And 24i, that's pretty long. That's going to be up here. And check it out. If you continue this line, look at that. That angle combined with itself. And now, let's square the two and check to see if they do indeed become 5 times 5, a distance of 25. So 7 squared is 49. And it's negative 7, but whatever. And 24 squared is something I don't want to do. Let's do it anyway. Let's switch colors real fast. 24, 4 times 4 is 16. 4 times 2 is 8, 9. 2 times 24 is 48, 480. So 96 plus 480 is 576. Alright, what's the square root of 576? Oh, wait. No, that's not the square root of 500. This is our first square, and our other square is 49. So it's 49 plus 576. So if you multiply those, add those together, I mean. Alright, that's 600. 9 plus 6 is a 3. Nope, why did I say that? Alright, so it's a 5. And that adds an extra 1, so it's an 8. 8 plus 4 is 2. Yeah. 625. Alright, let's take the square root of that guy. It should, by our estimate, be this number squared, 25. Let's check it. What's 25 times 25? 5 times 5 is 25. 5 times 2 is 10, so 125. 2 times 25 is 50. 500 right here. 500 plus 125 is 625. You should be amazed right now. We got the exact same distance. So we just proved basically 2 points. Multiplying two complex numbers together adds the angles together, and their distances multiply. Amazing. Alright, one more video, and we're going to prove one of the coolest formulas, I think, in mathematics called DeMoivre's theorem. It's going to be great.